the force of friction always acts tangent to the surface. Okay, and also in the direction that resists the pending of movement, right? For example, if we exert the force P on this direction, then the friction force must resist the movement. This box is tend to move to the right hand side. Therefore, the friction will move to the left side, tangent to the surface or to the floor. Okay, so we have friction. So in this chapter, we will study the effect of dry frictions, or sometimes it is called Coulomb friction, that named by the physicists who study this characteristic. And the dry friction occurs between two contacting surface body without any liquid. Because sometimes in the mechanic parts, we have to use lubrication oil to make surface more smoothly. Okay, another type of fluid, another than dry friction, we also have fluid frictions that occur between the contacting surface body when there's between two fluid surface. For example, between water and oil. Okay, between these two fluids, there is a friction. Fluid friction. And another type is internal friction. As is the name said, it is friction inside one body. So in this class, we will study the basics only with the dry friction. Friction that occur without any fluid. Okay, so let's see what is the dry friction and how we calculate the friction. From yesterday, we studied about the weight of the object, right? So one solid body, one rigid body, also have the weight act to it. And the weight is not acting just one point, but it is distributed all over body. However, all these system of forces can be reduced into one resultant force, W. And the position that this force, the weight acting on this body, is at the centroid. For symmetric shape body, the centroid will act at the center. Okay, so for this square box, the centroid of this body is at the center. Okay, so we have the weight of this box, W. So suppose that we also exert the force P, trying to pull this box on this direction. From the previous class, we will assume that the floor is smooth, so there's no friction. But today we're gonna discuss about friction, so we have to pull this force at this block along the love surface. Okay, this force is the love surface and also non-rigid, or it can be formable. Okay, we use deformable floor because it's clearly see the characteristic of friction. The floor is deformable, but the box is a rigid body. Okay, of course, we all know that their friction occur between the contacting surface, but what is friction look like? Because if we consider from the weight is distributed force, right? Because contacting surface is not just a point, but an area. In the same manner for friction, it distributes force too. Okay, a system of force, not just only one point. Okay, we have force acting on the floor. And while the weight is acting on the floor, they also have reaction force that resists the weight, pointing up to the box. Okay, we said that the weight is distributed force. Therefore, the N, or normal force, reaction force, also distribute force too. Okay, so here are the system of normal force. So why the N, or the normal force, are not equal at each point? Please imagine that while we are pulling this force P, and also the force is deformable body. Okay, the force can change its shape. Therefore, the area that near to the force P get more weight than this area that's further from the force P. That's why we have this kind of distributing load of normal force. Okay, the normal force varies. The further the area is, the smaller the normal force becomes. Okay, so we have the system of normal force, like the weight. This normal force can be reduced into one resultant normal force, NR. Okay, so let's consider this figure first. If this box is not moving yet, then this system is in equilibrium. That's why we can consider by using equilibrium equation. It's in the coplanar system, only xy, then so sigma fx equals 0 and sigma fy equals 0. For x-axis, we have the force P and the friction that resists this force. So P and minus delta Fn equals 0. Assume that this delta Fn represents all the friction force. Along y-axis, we have the weight W acting down, so W is minus. But for the normal force, let's have delta Nn as the represent of our normal force. It's acting upward, so delta N is positive. Delta Nn minus W equals 0. Okay, now we have two equations for equilibrium system. Okay, so what happened next? I want you to zoom in along this part between the floor and normal force N. Okay, zoom in this area and enlarge the part. The floor is large, so it's not just a straight line, but it has valley surface, valley height. And also the rigid body is not slab too, so it's not just a straight line, but look like this. Okay, so the force N will occur at the contacting surface. So only the point that contact to the floor has normal force N acting on it. In the same manner for F, the friction force, it will occur only at the contacting point. Okay, so we have friction acting along minus x and delta n acting along plus y. So these two forces, F and delta n, can be reduced into one resultant force acting on this position, right? So let's suppose that the resultant force between the friction and normal force is represented with delta R. Okay, and as we mentioned before that the system of this force, normal force, can be reduced into one resultant force acting at the centroid of the body. So the normal force is not acting at the center, right? Because the centroid of this type of loading diagram will slightly left, slightly on the right hand side. That's why we can rewrite this system again with this equivalent system. The weight acting at the center, but the normal force N acting at the centroid. Suppose that the position of the centroid measured from the center of this box equal to x. And force P acting on this box has direction of h, measured from the floor. We already considered the equivalent of force. Now let's see the equivalent of the moment. Sigma m about any point equal to 0. So you can choose any point, but you have to think about the reality, right? When we exert the force P to this box, the box is tend to rotate by using allow this area as a pivot. So you can choose this point too, right? But if you choose this point, there are 3 moments that you have to consider. It's like too much. So I will use this point. Let's call it point O, so that I can get rid of both force N and F because it's passing to the rotation point, and left only the weight and force P to calculate the moment. For these two forces, W, if we use a right-hand rule, the moment will rotate about counterclockwise direction. And for P, also use the right-hand rule, the moment will rotate in clockwise direction. It's turned in opposite direction, so we can just make it equal to make this system satisfy. For W, for M, equal to FD. D is perpendicular distance. So for W, MW equal to W and distance equal to X. And for P, okay, the force equal to P perpendicular distance you must measure from the floor equal to H. And like yesterday, we can calculate the distance or the centroid of this loading diagram X by just move the build to another side. So X equal to PH by W. when here we have the centroid of N. Okay, so when you study the friction while you're studying high school, you will just put the N at any point, right, to make it more simple. But for the rigid body, you must remember that the force M that the force N, the normal force N, that acting on this body is not acting at the center, but has a distance about x from the center. And also you have to consider about the equilibrium of moment. For any object that you insert the force to it, okay, there also the friction occur. Okay, so while you were increasing the force P and try to move this box, there are three possible motion: impending motion, motion, or in statics. Okay, in case where the surface of the contact are slippery, the frictional force F may not greater enough to balance P, right? Because you have to make P and the force, the friction force F equal. So if P is greater than the friction force F, this box is tend to move. And also the direction of movement is the same as P. So we can say that if P is slowly increased, then the frictional force F is corresponding increase too. Until it reaches one point, let's say Fs max. Okay, when we insert the force P and increase the force P until it reaches the friction force max, this object will start to move. At this point, we will call that this system is in limiting static frictional force. After we reach the Fs max, if we're still going to increase the force P, then the mock will start to move, right? And Fs also increase into one point. So the value that Fs reaches the final state is a box on this point, Fs max. It is the final point of equilibrium system. So if the friction force is go further than this value, then this system is not equilibrium anymore. From this experiment, the limiting static frictional force Fs is directly proportional to the resultant normal force N. Okay, so we have one constant, and that constant is mu s. That is coefficient of static friction. We will use this mu s just only in case that the system still in static system. Okay, now let's go back to this free body diagram. As we mentioned that the force N acting along y-axis, but the friction acting along minus x-axis. So these two forces can be reduced into one resultant force, Rs, having the direction of phi s, measured from the horizontal axis. So this system form one triangle construction. So we can use trigonometric method to find this angle phi s using arctan. We have phi s equal to arctan fs by n. And we can also replace fs equal mu sn into this equation. Okay, the n will cancel out. And we have only mu s left. So you can see that the angle phi s can be found by just using arctan mu s, only one value. And we're going to call this angle phi s as the angle of static friction. Okay, so in this state, we are still in static system. Now let's see, if we still increase this force P and make it reach the value point Fs. So this block will start to move, right? Then in the second state, motion. Okay, in this table, just show you that the static coefficient mu s is valid if you change the material. Okay, now in case of motion, the static friction Fs will become the kinetic friction Fk. In the same manner, Fk is directly proportional to the normal force N, but the constant will become mu k, that is coefficient of kinetic friction. Okay, so we want to make this block move by increasing the force P. That's why when the force P is greater than Fs, the box will move. And friction between the floor and the blocks is Fk. So what happened on this state? Let's zoom in this area and have this free body diagram. We still have the normal force N and the frictional force F at the contacting surface. But what happened is, when this block is start to move, the block will lie on the top of this peak. Okay, it will lie on this peak. Okay, when it's lie on this peak, it means that the contacting surface between these two surfaces are reduced. That's why it makes the Fk become smaller than Fs. Okay, because when you place this box on the floor and make it stay still, the contacting surface is larger than when you move this box. Okay, so Fk is smaller than Fs. Normally, the value of Fk, okay, let's go back to this equation. Fk equal to mu Kn and Fs equal to mu Sn. Normal force still the same, so Fk and Fs depend on mu K and mu S. So let's compare between mu K and mu S. Fk can be smaller than Fs, just in only one case, that mu K is smaller than mu S. So in this case, normally the mu K is said that it will approximately 25% smaller than mu S. Okay, so it is mu K is about 25% of mu S. Just approximate value, not the exact value. Like in impending motion system, the normal force N and frictional force F can be reduced into one resultant force, delta R. And this delta R acting with N along phi K direction. You can also find this angle by using trigonometer method. K is from one triangle. So you can find this angle by using arctan. Okay, that is arctan Fk by N, where Fk equal to mu Kn and N cancel out. Just have mu K left. Okay, so mu K, this phi K will become the angle of kinetic friction. Okay, in this slide, it shows you the relationship between the force P that you exert to the box and also the friction force that happen when you start increase this force P. Okay, so at first, both force P and friction force equal to 0. And after that, we start to increase the force P. In corresponding Fk or Fs, let's say it's both friction. The friction will also start to increase as well with the constant slope. So it's approximately F equal to P because it have to balance. Yeah, it must balance equilibrium system. So P equal to delta Fn. That's why frictional force and the external force must be equal. Okay, so let's increase the force P until it reaches this peak point. At this point, we reach the limiting of static equilibrium system. Okay, so if we continue to increase P after we reach this point, the object will start to move at the direction that the force P exerts. Like I explained before that if this box is start to move, it will lie on the peak between the contact surface. Therefore, mu K will reduce from mu S about 25%. That's why in this state, the graph will drop down a little and then become constant as Fk. Okay, at this state, Fk still constant, the same value. But after that, if we increase the force P great enough to increase the speed of this box, so as the force P becomes greater and the speed of the motion is high, then the kinetic frictional force Fk and the coefficients Fx mu K will begin to decrease down. Because this is due to the effect of aerodynamics. That if the box is moving greater enough speed, the air will support the movement between the contacting surface. Okay, the contacting surface reduced, so the frictional force Fk is reduced in the same manner. That's why along this state, Fk graph will drop down. This slide conclude all the characteristics of dry friction to you. Okay, I already explained all of them on the previous slide. So just list and try to understand again. Okay, by using this system of box, and insert the force P and see how it's moved, it can be classified into 3 types of static problems that involve dry friction. That are no apparent impedance motion, impending motion at all points of contact, and sometimes it has impending motion at some points of contact. Let's see the first case. In case of no apparent impending motion, or the first state of this graph, where the object is in equilibrium system. So of course, at this state, the frictional force that happens between the contact surface is static friction, Fs. From this graph, the object will stay in equilibrium system if the force P is smaller than Fs max. So from F equal to mu n, the object will stay in this state, no apparent impending motion, in case that Fs, not the friction that happens between the contacting surface must be smaller than mu Sn. Otherwise, the slipping will occur and the body will not remain in equilibrium anymore. For example, let's see this system. Here we have 2 bars, AB and AC, connecting at point B. First, every time that you want to solve some problem, you need to draw its free body diagram. For this object, you can divide this object into two parts, AB and BC. So we have two free body diagram. Okay, AB, BC. Each bar also have its weight acting at the center, W1, W2. With the force W, we must insert the normal force N to support the weight. Let's say NA and NC. We can use the support reaction method. The tip of this slot is allowed N. So the contact surface is just a small area. Therefore, the normal force will act at the direction that it will perpendicular to the contacting surface. So it just acts upward like this, NA and NC. In this system, we don't have any external force that insert to this system. So it has only the weight of AB and BC that make these two lots tend to move. So if you see this system, if the weight is greater enough, you have to guess where these two lots are going to move to. Like seeing from this weight and these two lots connecting at point B. So the tenth of lot of movement of AB is to the left hand side, and for BC, it tends to move to the right hand side. Then you have to exert the frictional force opposite to this direction, FA and FC. Not only the floor and the lot, at the connecting point B, it also have the reaction force between these two parts. Or you can say that the reaction force that occur from the support B. So we have two reaction force. And at this point, the lot AB and the lot BC must have the reaction force that act on the opposite direction to maintain the equilibrium. It will cancel each other. So let's suppose that Bx of AB acting in this direction. So Bx at BC act on the opposite direction. The same as Y. One will act up while the other will act down. Okay. However, although we have Bx and By like this, when we connect these two lots together, these four forces will cancel each other out, or it can be determined as internal force. So we can just consider this system, the weight and frictions and normal force. Now we have four unknown variables to solve if the weight is known. FA, FC, NA, and NC. Okay, so to satisfy this system, no apparent impending motion, we said that the frictional force must be smaller than mu n. Then from this system, these two bars will stay in equilibrium if FA is smaller than 0.3 NA and FC is smaller than 0.5 NC. Okay, sometimes it can be equal. If it does exactly reach the maximum point, it's not moved yet. Okay, but it's in a critical state of movement. Okay, so if these two conditions have satisfied, the system still remains in equilibrium, and it can be considered as no apparent impending motion. In case that motion is impending at the points of contact, so it's like it reaches the critical point. The condition of Fs must be exactly equal to mu Sn. It's about to happen, but not happened yet. Or we can say that the frictional force at this point is at a limiting static friction force. Let's see this system as an example. So suppose that we have a bar placing against the wall and the floor. So what is its free body diagram anyway? Of course, the wedge occurs at the center of this bar. And between the contacting surface, it must have the action force, normal force N, NB, and NA, acting to the body and also perpendicular to the contacting surface. In this system, we don't have any external force exerted to this bar, but consider from its weight and the gravity force. The gravity force effects will make this bar AB tend to move to the left-hand side. That is, at point B, the bar will slide down, so the friction must exert to support the sliding, FB. And at the floor, at point A, the bar is tend to slide to the left-hand side, so the friction force must produce to support that, FA, in this direction. Okay, so to satisfy this condition, FA must be exactly equal to mu A and NA, that is 0.3 NA. And for FB at point B, it is must exactly equal to 0.4 NB. Okay, so you must satisfy all these two conditions to make this system is to become impending motion at all points of contact. The last case is called impending motion at some points of contact. Some may move, but some may in static condition. So let's see this system. If I exert the horizontal force P to this bar BC, and to cause the movement. Okay, so first let's draw a free body diagram. We need to separate these two bars out of each other. So we have A, B, and the bar BC. We have external force P at BC, and each bar have the weight effect W. Okay, we have reaction force of the support at B, acting on different direction. At the contacting point A and C, it has normal force in A and C. Now let's consider the movement, the tend to move direction. We exert the force P to the right hand side. So both BC and AB will tend to move to the left hand side too. Oh, sorry, the right hand side. Then the friction must act to the left hand side for both bars. Okay, so after you have the free body diagram and then state of force that acting on this free body diagram, you have to guess the situation. Like in this case, it can will cause two possible cases. The first one, if we exert the force P and it has slipping at point A. And then no slipping at C. Or in other case, the slipping occur at point C, but no slipping at A. Okay, and let's consider why can these two cases happen. Like for the first case, the slipping at A will occur if FA is smaller than or equal to 0.3 NA. And for FC, it's not slipping, so it might reach the maximum state or less than 0.5 NC. For the second case, the slipping at C occur, so that FC must be equal to 0.5 NC, like it starts to slip. And for FA, the frictional force must be smaller or equal to 0.3 NA. Now, to determine the actual situation, you have to calculate the force P for each case, okay, and then choose the case that provides smaller P. For example, if you can calculate the P as for case 1, you can calculate P equal to 3 Newton. And for case 2, you can calculate the force P to 5 Newton. Then you have to choose the smaller P because it will happen first, right? Because the force P must reach 3 Newton before it reaches 5 Newton. Then it shows that case 1 will happen first. Then in this system, it will slipping at A and not slipping at C. Or on the other hand, if we switch, we have case 1 equal to 5 Newton and case 2 equal to 3 Newton. If you can calculate like this, it means that case 2 will happen first because it reaches 3 Newton first. So in this case, it will slipping at C and not slipping at A. So the important point is that when you solve the equilibrium problem, you have to consider every case that can occur for that system. And then after you can determine the frictional force of its contacting surface, then finally you can predict the actual situation by comparing the coefficient of frictions or sometimes comparing the force that exert to the system. Okay, so the important point is guess how this motion is tend to move. Okay, and then you can predict the direction of frictional force and help you to solve the problem. Let's see one simple example. Okay, this question asks you to determine if it remains in equilibrium or not, and also determine one thing. Okay, so the coefficient of static friction is given as mu s equal to 0.3. First thing first, when you have any problem, don't forget the free body diagram. Okay. It's in basic geometry shape, so the weight is acting at the center, W, equal to mg. Okay, we exert a force P in this direction. So the friction force must create to support that movement. Let's say F. And to support the weight W, the force must insert the normal force into this box, but it's not exert at the center of this box, right? Like the loading diagram that I explained to you before. The normal force will passing to the centroid of the loading diagram, and also the position, it shifts near the movement direction. So let's suppose that if normal force N acting at the point has distance of x from the center. Okay, so now we have all the force on this system. Then we can get this force and set into equation of equilibrium. like Fx equals 0 and Fy equals 0. And also, if necessary, you have to set the equilibrium of moment too. Sigma moment equal to 0. Okay, so please determine the frictional force F and normal force N. Okay, so how much is the friction force? So I can calculate friction as 69.3. And normal force N, it is 236.2 Newton. Okay, so next we have to determine if the box is moving or not. In case that the box is moving or in the state of moving, the friction force Fs must be greater or equal to 0.3 N. Okay, N is the same, so we can just substitute this N into this equation. In this case, I can calculate Fs max equal to 70.9 Newton. So let's compare between the friction force that occur in this system and the maximum friction force that it can contain. So you can see that the friction that happened in this case is smaller than the maximum Fs, although it's also very close. But it is smaller than Fs, so this box is not moving yet. Then it is still remain in equilibrium. Okay, so first you have to calculate the mu(s) or the friction that actually happened in this system, and then compare with the maximum force Fs and see that is this move or not. All right, so here are the concept of friction force. Now we can use this concept of friction force to determine like the machine part that we always see in the system. Okay, for example, we will apply the dry friction into the weight that we always use in mechanical system. So what is the wedges? It is a simple machine that is often used to transform and apply force into much larger force. For example, this system, we can just exert this small part and exert small force to lift this pipe, the big pipe. Okay, and this rate will have the angle. So we have to use the light angle to apply the force. And we can just slightly move or adjust the heavy load, like this pipe, for example. So let's consider this system. Okay, we use the wedge to support this box that placing against the wall. For this system, we can write the free body diagram by separating these two boxes out of each other. So we have the free body diagram of the wedge and free body diagram of the box. Okay, so for the box, if we exert the force P and increase the force, this box is tend to move upward. So the friction force occur between the wall is direct down, Fs. Okay, let's say F3. And we must have the normal force, N. Also the wedge that acting at the center, W. Between the contact surface of the wedge and the box also have friction. Okay, if we increase the force P, the weight is tend to move to the right hand side. So the friction will resist that movement, act to the left for the weight. And because these two surfaces contact each other, if the weight friction is act to the left hand side, so the box friction will act in the opposite direction to support that. So F2 acting on this box, direct on this direction. Okay, the same as force N, that it is action and reaction force between these two parts, is must act on the different direction. If I suppose that N2 acting on this box is upward, so to the weight, N2 will act downward. And lastly, between the floor and the weight, also have friction. This is the movement F1 and normal force N1 with external force P. Okay, so we have the free body diagram of this system. I forget to mention this. Generally, we will neglect the weight of the weight because if you can see the system, the weight is smaller, greater smaller than the object that we want to move. So we can negate the weight of the system because it affects the system in a very small effects. So just negate the weight and care only the weight of the object. Okay, and then just solving the problem by make the system into equilibrium system. Sigma Fx equals 0. sigma Fy equals 0, and also the moment about any point equal to 0. Okay, where all the forces, frictional force, equal to mu n at each point. Okay, but to determine the free body diagram of the system, you have to guess where the object is tend to move. For example, if we are not increase the force P, okay, so no force P, but these systems can still remain in static state. We will say that this system is a self-locking system. Or sometimes this force P can be exerted in the opposite direction. Right, the force P can be act in this direction. In case that you want to, you are trying to move this weight out of the system. Okay, then the movement will change, right? Because if we exert this force P, the weight will move to the left-hand side. Then the frictional force will act to the left-hand side. Okay, so the friction force are not necessarily to acting on this direction. It depends on the force P and the length of movement. Okay, here is the first application of the frictional force in mechanical system. Next, let's see if we apply the frictional force on a screw. Okay, in most cases of mechanical system, the screws are used to fasten or make two parts attached to each other. But in many types of machines, they are used to transmit power or motion from one part to the machine to another. For example, the wheel to open the valve. Okay, we need to transmit the rotation movement into the translation movement like this. So in this case, in mechanical parts, a square head screw is commonly used for this purpose. So let's analyze the square head screw in this figure. So if we zoom in just only one part, only one turn of screw, so you can see that it looks like we have a cylinder that wrapping with this part, a triangle part. So let's remove this part and unwind to this figure. You can see that it's like the triangle construction. So let's assume that we don't care about this angle, but let's see just a big picture, this triangle. Okay, so if we assume that this area is full and we have this big triangle, we can design the thread angle theta by using arctan. Okay, this arctan L and divide by 2 pi r, which is the length of this cylinder. Okay, sometimes this length L is called the lead of the screw because it shows the distance that the screw can travel if you turn one revolution or turn one round 360 degrees. And how can it travel? Okay, so from this construction, we can also guess the motion of the screw. In case that screw is tend to move upward, okay, we give the force bill and also insert the moment to turn this screw. So the movement will, the movement of the screw, one screw, will act to the right hand side. That's why we have the frictional force act on this direction. Okay, so just consider just a small section like this one. For this screw, we have one force exert to turn this screw equal to M by R. So how can this become M by R? Let's go back to the moment M. We all know that the moment equal to the force and multiple with the perpendicular distance. So for this moment M, we don't know the force yet, right? But for the distance, this moment M is turning around the center point. So the distance between center point and the edge of the screw equal to the radius R, MR. So F that's acting on screw equal to M by R. Okay, so we have this force acting to the screw. For this part, the frictional force and normal force can use to form one resultant force R, right? And we can also determine this angle phi s by using this construction. Then phi s equal to arc tan F by N. Okay, and then use this angle to resolve N and R or F into each component along X and Y. Okay, now next, let's set into equilibrium system. Sigma Fx equal to 0, sigma Fy equal to 0. For example, let's see Fx. For Fx, we have M by R act to the right. And the force that acting on another direction is F, right? But we have to resolve the F and make it Fx first. Okay, you can use F or use R. Okay, if you use F, you have to resolve two forces, F and N. But if you use R, you resolve just only one force. So I will use R. Okay, I will let's resolve this force R and make Rx. So sine the angle. For the angle, not just only phi s, but you have to plus with theta too, okay? Because here the angle. Can do the same with FR. In y-axis, we have the bill and resolve R into y components to balance that. Okay, we have equation in x and y components. And for these two equations, you can rewrite the form again to find the moment. Rewrite into this form. And you can find the moment that acting on this screw to make it tend to move upward. Sometimes the screw can lock by itself. We call that the self-locking screw. So we don't have to exert any force because it can lock or balance itself. So for this self-locking screw, we can draw the free body diagram as this figure. Okay, to make a screw in self-locking state, this equation must be satisfied. That is, the phi s must be equal to the angle theta n. Okay, then the screw becomes self-locking. Only two forces to consider, W and R. And the last, if the screw is tend to move downward. Okay, there are two cases. The first, in case that we have to exert the moment to make the screw tend to move downward, we can write the free body diagram as this, the left-hand side figure. And if the screw is in the self-locking state, but it starts to move downward, we will have this free body diagram. So use the same method again. Resolve all force into x and y component. Set into the equilibrium of system, Fx equals 0, Fy equals 0. And then rewrite the equation in the moment form. We have this equation, m dash. The m dash we must exert to balance the system. And m double dash, if the screw is self-locking state, but it tends to move downward, then use this equation. Okay, to make it more clear, let's see one example. We have one turnbuckle here and insert the moment M, the direction as shown in this figure. And when we turn the moment M, the screw above tend to move up, while the screw below tend to move down. The lead screw is given. Okay, the radius also given. And this question asks you to determine the moment M that must be applied to draw the end of screw closer together. Okay, so in this state, you have to choose the right equation. Okay, like this one. We insert the moment to make the screw move. So we have equations M equal to RW tan theta plus phi s. But not only one moment, right? Because we have two screws to handle, above and below. So it must multiple with 2. Okay, so everything is given, like the force W equal to 2 kilonewton, so 200 Newton. The radius also given, 5 millimeters. And mu s to 0.25. The lead or L equal to 2 millimeters. From the first page of the school, here, we can find the angle theta by using L and R. So theta equal to arctan L by 2 pi R. And what about phi s? Phi s is phi s is the angle between the normal force N and frictional force F. So we can find phi s by, okay, let's just go back to this page. The phi s, or the angle between the normal force N and the resultant force R, can be found by just use arctan of the coefficient of static friction, arctan mu s. Okay, so here we have everything we need. We can find m by just substitute all value into this equation. So in case that you have question, why we choose this equation? Because this equation is when the screw is tend to move upward. Just zoom in the system. Okay, for the upper screw and the lower screw. It is easier to consider the upper screw, right? Because it just look upward. And consider from the force, 2 kilonewton is given as this direction. So you can guess that the screw is tend to move up. That's why we use this equation. Okay, so for this system, we have M equal to 6.37 Newton meter. Okay, another application on mechanical system is the frictional force on the flat belt. It's like we exert the tension to the lobe, and between the contacting surface of the lobe, there are friction. For example, this system, we want to exert the force T2 and try to move the belt to the left-hand side. So you can see that the tension T2 that we exert to this belt must be greater than T1. Because if we want to move, not only T1 that we have to overcome, but we also have to overcome the friction between these two contact surfaces too. Like T2 is tend to move to the left-hand side. So the friction force that happen act on this direction. So T2 must be at least equal to F plus T1, approximately. So for this situation, they already give you the ready-to-use equation, like T2 must be equal to T1 E power mu B. If you want to know how can this equation become like this, you can check in the textbook. It's quite take time, so let me skip the step. Okay, so you have everything you need, like the coefficient of static frictions and the angle of the contacting surface. Then just substitute into this equation. For example, this question is asks you to determine the largest mass of this cylinder that it can lift by this cord. Okay, so first you have to determine, you have to write the free body diagram. So for this system, we all know that the tension force is equal along the line. Right? But we can skip the system in the middle because it is a pulley. So there are no frictions here. Then we can just consider this to free body diagram. Okay, for example, let's see this one. It is T2 and here is T1. So we all know that T2 is equal to T1 E power mu beta. Okay, so your job is to find the contacting angle beta. The mu is already given. So let's just consider from these figures. Of course, the contacting surface around this point, 90 degrees. And what about this point? Okay, then you have to use this triangle construction, right? 45 degree, 45 degree. And it's all effect to another side. Then for this system, beta equal to 135 degree. Okay, and then replace to this system. Okay, I forgot to mention that this beta must be calculated in radius unit. So you have to transform 155 angle into radius and then substitute into this equation. Okay, so we run out of time. I will give you the answer for these questions. M is 15.7 kilogram. Okay, for the first one, just use the equation and then do the same method with this side. But the T2 will become the weight of this cylinder. Okay, so for today's class, do you have any questions? Okay, if not, I will let you prepare for the next class. Okay, and see you next week. One homework for today. Okay, we have the distributed loading acting on this lot, and also you have to consider the frictional force. Okay, so let's sum up the class for today. Thank you for coming and see you next week. Goodbye.